to remember the 3 different ways of charging. So those are,
Charging by friction.
yeah, but try and do it without the notes. Charging by friction, induction, which means what? When it doesn't touch, and then conduction, which is when they touch. And then they share their charge. And when they share their charge, how do we figure out the new charge? Add it together. Okay, so new charge. After conduction. So if I have 2 charges that come in together, this is 3.2 microcoulombs, and this is, let's say, negative, and this is 6 microcoulombs. It's negative 3.2 plus 6.0. There's 2 of them, so we divide by 2. Of course, I didn't pick an easy number. 9.2 divided by 2, 4.5, 4.6? No, 4.5, 4.6. Oh no, it wouldn't be. Hang on. What? Okay, but what was my error? What? It was negative. Okay. So then that gives me a charge of what? 2.8 divided by 2 is 1.4. Positive or negative? Positive 1.4 microcoulombs. Okay, but you take the 2 charges and you add them together and then divide by 2. So don't forget that piece. This is obviously a common error if I'm forgetting it. Okay? You need to understand how electrons move between a conductor versus an insulator. So that was where we looked at if this was and then what would happen when we brought in another one, right? They would rearrange themselves. You would have all the negatives on one side. And this one here would have all of the positives. Because what moves? What can move? Electrons. Okay? The electroscope, so that's this box with that little ball on the top and it has the leaves underneath of it. So if I brought in a rod that was charged negatively, we would see the positives be here and the negatives be here, and then we would see what? What would we see the leaves do? Yeah, they would spread apart, they would repel. Okay? Coulomb's law we touched on, so that's the formula Fe is equal to K Q1 Q2 over R squared. And it's, if we looked at a graph between force electric and R, we would see what kind of graph? Yep, it's inversely proportional. If I looked at a graph, paying attention to my labels, if I looked at a graph that said R squared, 1 over R squared, what would my graph look like? Yep. Okay, it would be a straight line, it would be linear. Because that is the actual relationship, right? The formula is Fe is equal to K Q1 Q2 over R squared. So we're looking at the relationship between Fe being proportional to 1 over R squared. Because this is the direct relationship, Fe. But if I do this, where I look at Fe being proportional to R, then that's where we get the loop, because it's actually, this is a denominator piece. Okay. When we look at equations, when we do the math, Q1, Q2, we do not include charges. Q1 and Q2 charges simply tell us, if we're looking at two pieces, this one was a positive and this one is a negative, what's going to happen in this? This is going to be an attraction, right? So the force is going to go in this way. The electron will move that way. If I had two charges that were positive or negative, it would be repulsion. And so the force would move this way, right? They would move apart. So that's what the signs tell you. The signs tell you how things move. This is not electric fields, because clearly we know an electric field actually moves which way on a negative. It goes in towards the negative. But here, when we're looking strictly at attraction and repulsion between two charges, we're looking at what's moving. Well, the only thing that can move is the electron, or the negatively charged particle. And so it will move towards the positive. This is a sign of attraction. This is a sign of repulsion. Two negatives, you would also have your signs look like that. Okay? So when we're doing electrostatic force, the charge signs simply tell us which way it's moving. Is it attracting or is it repelling? When we're looking at net total net force and the direction on the charged objects, pretend that the charge you're trying to find the net force on is mobile and all the other charges are stationary. So that's this one here. If I had 3 and this one was positive, positive, and negative, the net force, what's happening here? This is a repulsion. If I was looking at B, well, it's going to move this way, right? It's going to force A away. What's it going to do to C? It's going to attract. So your net force would be these two values going in the same direction. You just have to know, put your star where, what is it being acted on, okay? And the question is usually pretty good at identifying that piece. We looked at 2D problems and linear problems. So if I was to look at a linear problem, okay, A is positive, B is negative, and C is positive. So in this case, let's make C where the net force is acting. In terms of B and C, which way is the arrow going to go? It's going to be an attraction force. It's going to be an attractive force, or you could pull it in. And then if I looked at A on C, let's do it the other way, because that's how we've been doing it. This is going to be opposite, so if you're looking online to the notes, this is going to be opposite, but it's the same thing. We're not changing things. We're just making it relative. Okay. We say that the negative is what moves, so it would attract that negative charge into it. That's all we're doing. We're just sticking with the same language. What happens to A and C? What do? They repel. So FAC is actually going to be a repulsive force. So if I looked at F net, it's going to be FBC because it's positive. Oh, sorry. Minus FAC, right? Because BC is moving in the positive direction and AC is moving in a negative direction. It's moving to the left. It's got nothing to do with that it was a positive or a negative charge, just direction only. Okay, a 2D. Okay, negative, positive, positive. And we're looking at the net force here. So what's going to happen between AB? Attraction, right? And it's the negative that moves. And then what about between B and C? It's going to be repulsion, so it's going to move away from. Okay? So then how do we figure out the net force? This is going to be what we're looking for. That's the overall net. So it's going to be the square root of, this is force AB. This is going to be force BC. So it's force AB squared plus force BC squared. And you solve that using the K1 Q2 over R squared, KQ1 Q2 over R squared formula. And these also require an angle for your direction. Okay? Force is a vector quantity, and so it needs a direction. And then we also have the option to look at free body diagrams. So here, if this is my ceiling, here's my negatively charged plate. I have a pith ball that is suspended, and it's a negative charge. So we're going to see electrostatic force do what? Repel. So it's going to move the pith ball this way. What are we going to see the force of gravity do? It's going to go straight down. And then we have this piece here where it's attached to the string. We have force tension. Okay? And we always redraw it tip to tail. So if I start with force electric, and then I do force of gravity, my tip to tail here is my force tension. Okay? You could start with force of gravity first if you wanted. And then you could do your force electric. And what we see is the exact same line for force tension. The thing that you need to be able to translate properly, though, is, not that one, this angle here translates into this angle here, or this angle here. So depending how you draw your diagram will depend where you put that angle. Okay? Does that make sense? No? So here, if I draw my force electric first, and then my force gravity, and this angle goes here, but if I draw my force gravity first and then my force electric, I need to remember that that angle is still outside of my triangle. But then you could figure it out, right? Because you would go 90 minus theta equals your angle that you need. Okay? And then we all know, because now that we're in a triangle, you would use Pythagorean to solve. And trig, because you need that angle to solve. Okay, so you need Pythagorean and trig to solve. So that was like the first 3 maybe lessons that we looked at doing. Then we moved into the guts of it. Okay, we started looking at electric field lines. And this is where we need to pay attention. On a positively charged ion, the electric field strength moves outwards. On a negatively charged particle, the electric field strength moves inwards. So it flows out of the positive and into the negative. And so then we can start looking at great big field strengths. So we didn't change anything. It flows out of the positive here. It flows outwards here. And it flows inwards here. Okay? Same thing, if I have 2 of the same charge, this one's positive, it's flowing out. This one's flowing out. In this space here, there is what? There's no electric field in that dead zone. Okay? One of the things that we also need to note is the more lines, the greater the field strength. Okay? If I have a point that's producing the electric field, we're going to use electric field strength because that's the E with the vector over top of it. That's not energy. That's electric field strength. Is equal to KQ over R squared. But this is the key word if it's producing. Okay? We can look at it linearly and we can look at it in a 2D. So in a linear problem, if I have 2 charges, A and B, and I have some point somewhere inside of that, point P, okay? We're going to have, how does an electric field strength work with a positively charged particle? Well, you had a 50-50 chance. It flows out of the positive. I guess you were right, towards the negative.
Oh, that's oh.
Okay? And it will flow out of this positive. So here, my electric field strength due to particle A is flowing this way. And my electric field strength due to the charged particle B is flowing that way. They're flowing in towards each other. Okay? So my electric field strength, point P, it's just some random point inside of those two charges. It's producing an electric field. Okay? So my electric field strength at point P is going to be equal to EA is moving in which direction, positive or negative? So EA, and then B is moving in which direction? Negative. So it'd be minus EB. Or you could say EA plus negative EB. They say the same thing. Okay? If I had a 2D, and here's some random point P, producing an electric field. From the negatively charged particle, which way is the electric field strength going to flow? In. So it's going to flow this way. Point P, it's going to flow which way? Yeah. No, this positively charged particle, which way is it going to flow? Outward. Okay? So you have to look at trig and Pythagorean theorem, but it's going to look like this. We call this A and this B. This would be EA, and this would be EB. So then our EP, that's not potential energy, that's electric field strength at point P. I know, super confusing, hey? No, they always call it point P. In any written document I've ever looked at, in any textbook on the diploma, it's always point P. I don't know why they picked that letter. I have no idea, Avery. But nothing like making stuff confusing when we're talking in letters E's and P's. Okay? We would have the square root of the electric field strength due to particle A squared and the electric field strength due to particle B squared. Okay? This is a vector, so you're going to need an angle and a direction. Okay? This is not, I'm doing this so that we know that it's not energy. We look at EK because it's got to be in motion. And our EK plays into our energy. So now we've got another E with a triangle out front. That's energy. And energy is always measured in what? Joules. So you need to make sure that you are in kilograms, meters, and seconds squared. You have to have those units. A joule is actually a kilogram meter squared per second squared. Okay, you have to be in those units. You don't get an option. Change in energy is final energy minus initial energy. And so then you could have EKF minus EKI. Okay? Is equal to. It's also the word voltage also is potential difference. If we see that word, they mean the same thing. That's why I wrote that there. Because sometimes we'll see potential difference and we won't know that we can use the V formula there. And in this lovely conversion, an electron volt that's what EV stands for, electron volt, is equal to 1.6 times 10 to the negative 19 joules. So it might ask you for the results in electron volts. Typically, used when energy is really small. Okay, parallel plates. Some of the things that we have to remember about a parallel plate. Is that it needs a power source. If I see a power source like this side is negative, this side is positive. Okay, so if I cook my battery like this plate is going to be, the top one, negative. And my bottom plate is going to be positive. Okay. And so you could see this like this. You could see it written like this. They might simply do this. Put a B for battery. Which way is my electric field strength going to move? It's going to move away from the positive and into the negative. Okay? What do we know about electric field strength between uniform plates? What was that, Avery? Nope, that's potential difference. This is uniform. Electric field strength is uniform across the entire distance between parallel plates. What Avery is saying, if we look at over here, this plate is negative, this plate is positive. So the electric field strength is moving this way, but my voltage across it varies. Okay, my voltage varies between the plates. That was a good question, Avery. Okay, so we cannot use KQ over R squared. In parallel plates, never use KQ over R squared. What we can use is we can use electric field strength is equal to voltage or potential difference over distance. Electric field strength is equal to electrostatic force divided by charge. Or potential difference is equal to energy divided by charge. Okay, so this can be used in parallel plates. Projectile-like motion of charged particles in a uniform parallel plates. If you're parallel to the electric field, so if this is my electric field here, so what are my plates? Which one's my positive? Which one's my negative? So if I had a particle here that was positive and it was moving parallel, that's parallel to the plates, okay, it's accelerated. So remember when we did projectile motion? We had horizontal and vertical. Okay. So we're going to look here at parallel and perpendicular. And so I don't want you to get hung up on the word horizontal or vertical because it really depends on the orientation of the plates. I want you now to look at parallel versus perpendicular. In parallel, that's where we can find acceleration, right? D, V, T, and A. Over here, this is uniform under perpendicular. So again, we can use velocity, distance, and time. Same concept as horizontal versus vertical in a projectile motion. But now instead of saying horizontal and vertical, now we're using perpendicular and parallel. Because if I was going perpendicular to the plates, so perpendicular would be this way, because it's perpendicular to the plates, I'm actually moving in the same direction as what? If I was going perpendicular to the plate, what am I actually moving in the same direction of? The which? So we can always think of it as, am I moving with the electric field strength or against the 90 degrees to the field strength? So parallel or perpendicular to the plate. This is acceleration. Okay. Time and perpendicular, they talk. You solve one, you solve it in the other, remember? Same as in projectile motion, time is what talks between the two. But in projectile motion, you can only use the formula V equals d over t, right? So we're either looking for a velocity of a particle or we're looking for time. Typically, we're looking for time because it talks between the two. Force of gravity can be ignored for atomic, subatomic particles in parallel plates. So force net, being that it's force electric plus negative force of gravity, we can say that the force of gravity is negligible for a subatomic particle. So then in this case, force net could be equal to force electrostatic force. Okay? Time, I've already said time already talks between the two. All right, when we look at current, we learned one formula. Oh, you have a question? Sure. For zero, because when we're looking at subatomic particles, we're looking at charges that are 1.6 times 10 to the negative 19, or some multiple of that. We're looking at masses that are 9.11 times 10 to the negative 31, right? And force net is mass times acceleration, right? Anything multiplied by something times 10 to the negative 31, you're not going to see a change on. It's just such an obscurely small number. So force gravity doesn't really play into. You've got 9.81 trying to attack like a speck. It just doesn't have an impact on it. Okay? It's a good question. All right, current Q over time. In this one here, we were introduced to solving the number of electrons. Thank you. Okay, number of electrons is Q total over the Q of one electron. So this Q here will solve Q total. Last thing that we learned was Millikan's oil drop experiment. Okay. So you always start with a free body diagram to determine the direction of the forces acting on the particle. We cannot ignore the force of gravity because it's not a subatomic particle. An oil drop, it's like sucking up 5W30 into an eyedropper and then squeezing out a drop. It's that same thing. It's not subatomic, so we can't ignore gravity. So if a particle is stationary or constant, this is keyword constant or stationary means what? Force net is 0. Okay? So here's two scenarios for you. Here's my two parallel plates. Top one's negative, bottom one is positive. If I put a positive particle in here, gravity works which way? Down. And the electrostatic force is going to be equal to, or is going to be moving in which direction? This positive particle, which way is it going to go between these plates? Up, because of the force of attraction, right? So here, if force net, this is our options here. Force net is equal to force electric plus or minus force of gravity, right? So in this particular scenario, if force net is equal to 0, that must then mean that force electric is equal to force gravity. Okay? It's either being, back in physics 20 when I asked you, is this object going through the floor or being levitating? And it wasn't. It was like on the ground. Force net was 0. Okay? What? No. Okay, let's switch the plates around. See if your brain can make the switch. And I put a negatively charged particle in here. Force gravity moves which way? Down. And force electric is going to move which way? Up because of attraction. Force electric is equal to force gravity. All right. If a particle is accelerating down, okay, and I put a negatively charged particle in here, we have acceleration, which means that we now have force net. Force net now does exist. Okay, the minute we see acceleration, right, force net, mass times acceleration, we're in motion, we have force net. Which way is gravity working? Down. Which way is this charged particle going to move? Down. Okay, so in this particular case, force net is going to be equal to force electric plus force gravity because they're moving in the same direction. You could say negative force electric minus force of gravity. It doesn't matter. They're moving in the same direction. Same idea here. And I have a positively charged particle. Gravity moves which way? Force electric's going to move which way? The positively charged particle is going to go to which plate? Down. Okay, same thing. Force net is equal to force electric plus force gravity. All right, if the particle is accelerating up, and I put in a positively charged particle, what is going to happen? Yep, but force gravity is going to go which way? Okay, so force gravity is going to go down, and force electric is going to go up. Okay, this is where we've never really paid attention in all of our years to the length of the arrow. But remember, in one class, one time in Physics 20, we talked about arrow length indicating strength of a force. We did that. We did like it was 400 newtons pulling one way and 200 newtons pulling another way, and we had different length arrows. Force gravity, if this is accelerating up, if it's accelerating up, our force electric must then be stronger than our force gravity. Okay? What if I had this? And I had a negatively charged particle. Which way is gravity going to go? Electrostatic force is going to go which way? Okay? Make sense? This is your final chance to ask concept questions. Yeah, positive plus negative is the same thing as saying subtracting force gravity. This is the same thing as saying, it says the same thing. This is just how textbooks will always rate it, is plus the negative force of gravity. And a lot of people, they get confused because force net, like a net energy, a net force, a net anything is the sum of everything, right? So sum being adding. Okay, here we go. I'm going to turn the lights on. And as a group, either where you're sitting or move to another spot where you think you're going to have more brain power, however you want to do it, you're going to collaboratively move through these questions.
Like together?
Yeah.
Oh, I thought you said you have to go.
No. Why